This call is now being recorded.
Good morning, good afternoon, everyone. Today we are going to start our third unit, that is Francis turbine. Okay. So what is reaction turbine means? Reaction turbine means that water at the inlet of the turbine possesses kinetic energy as well as pressure energy. What is the meaning of reaction turbine? Reaction turbine means the water at the inlet of the turbine possesses kinetic energy as well as pressure energy. Okay. As the water flows through the runner, a part of pressure energy goes on changing into kinetic energy. Thus, water to the runner is under the pressure and the runner is completely enclosed in an airtight casing, and casing and runner is always full of water. Then what are main parts of radial reaction turbine? The main parts of radial flow reaction turbines are casing. First part is casing. Second part is guide mechanism. Third part is runner. And fourth part is draft tube. So first part is casing. This is the casing of your radial reaction turbine, and the casing is of spiral casing. Okay. Casing and runner are always full of water. The water from the penstock enters the casing, which is of spiral shape and in which area of cross section of casing goes on decreasing gradually. Area goes on decreasing gradually. The casing completely surrounds the runner of the turbine. The casing is of spiral shape so that water may enter the runner at constant velocity throughout the circumference of the runner. The casing is made up of concrete, cast steel or plate steel. Okay. Now the second part is the guide mechanism. Second part is the guide mechanism. It consists of stationary circular wheel. It consists of stationary circular wheel around the runner of the turbine. The stationary guide vanes are fixed on the guide mechanism. The guide vanes allow water to strike the vane fixed on the runner without shock at the inlet. Also, by suitable arrangement, the width between two adjacent vanes of the guide mechanism can be altered so that amount of water striking the runner can be varied. The third part of the radial reaction turbine is the runner. Third part is the runner. Here it is shown as runner. It is circular wheel. Okay, runner is a circular wheel on which series of radial curve vanes are fixed. The surface of the vanes are made very smooth. The radial curve vanes are so shaped that the water enters and leaves the runner without shock. The water enters and leaves the runner without shock. The runners are made up of cast steel, cast iron or stainless steel. They are keyed to the shaft. Okay. Now the fourth part of radial reaction turbine is draft tube. It is not shown. It is not shown in the figure, but the draft tube. I will explain the concept. The pressure at the exit of the runner of the radial turbine is generally less than the atmospheric pressure. The water at the exit cannot directly discharge to the tail race. A tube or pipe of graduation from exit of the turbine to the tail race, and this tube is of increasing area, and that tube is called as draft tube. That tube is called as draft tube. Now we will see some formulas regarding the Francis turbine. As we know, the work done per second on the runner by the water is given by the equation. Work done per the second is given by the equation rho A V1 into bracket VW1 U1 plus minus VW2 U2. Okay, as we know, area into velocity is equal to discharge. Therefore, I can write it as rho Q into bracket VW1 U1 plus minus VW2 U2, where VW1 is equal to velocity of whirl at inlet, VW2 is equal to velocity of whirl at outlet, U1 is equal to tangential velocity of the wheel at inlet, and the formula for U1 is equal to pi d1 into n divided by 60, where d1 is equal to outer diameter of the runner. Then similarly, U2 is equal to tangential velocity of wheel at outlet, and the formula is U2 is equal to pi d2 into n divided by 60, where d2 is equal to inner diameter of the runner and n is equal to speed of the turbine, and that is in RPM, revolution per minute. Now, the work done per second per unit weight of the water per second, that is equal to, means work done per second per unit weight of the water per second, that is equal to work done per second divided by weight of water striking per second, that is equal to rho Q into bracket VW1 U1 plus minus VW2 U2 divided by rho Q into G, that is equal to 1 by G into bracket VW1 U1 plus minus VW2 U2. Now, you know we will take positive sign when beta is acute angle. If beta is obtuse angle, we will take negative sign. And if beta is equal to 90 degree, then VW2 is equal to 0 and work done per second per unit weight of the water striking becomes as when beta is equal to our equation will become as 1 divided by G into bracket VW1 U1. VW1 U1. Now we will see what is the formula for hydraulic efficiency. Hydraulic efficiency. Hydraulic efficiency is equal to runner power divided by water power. That is equal to W divided by 1000 into VW1 U1 plus minus VW2 U2 and divided by W into capital H divided by 1000. So striking out the similar terms, we will get VW1 U1 plus minus VW2 U2 divided by G into H, where RP is equal to runner power, WP is equal to water power. If the discharge is radial at outlet, what it means? If discharge is radial at the outlet, when beta angle is equal to 0, at that time VW2 will become as 0. VW2 will become as 0. Therefore, hydraulic efficiency is equal to VW1 U1 divided by G into H. VW1 U1 divided by G into H. This is the formula for hydraulic efficiency. Now we will see some formulas regarding the radial reaction turbine. Okay. First one is the speed ratio. First one is the speed ratio. Speed ratio is equal to U1 divided by square root of twice GH, where U1 is equal to tangential velocity of wind at inlet. Then second formula is flow ratio. The ratio of velocity of the flow at inlet, that is V1, to the velocity given, that is square root of twice GH, is known as flow ratio, and it is given by the equation flow ratio. It is given by the equation VF1 divided by square root of twice GH, where capital H is equal to head on the turbine. Third formula is discharge of the turbine. Discharge of the turbine. The discharge through a radial reaction flow turbine is given by Q is equal to pi D1 B1 into VF1, and that is equal to pi D2 B2 into VF2 into VF2, where capital D1 is equal to diameter of the runner at inlet, diameter of runner at the inlet. Capital B1 is equal to width of the runner at inlet, and VF1 is equal to velocity of flow at the inlet, and T2 is equal to diameter of the runner at outlet, B2 is equal to width of the runner at outlet, and VF2 is equal to velocity of flow the wind. Then area through which flow takes place is given by, if we consider thickness, then area through which flow takes place is given by pi d1 minus n into t, where n is equal to number of winds on the runner and small t is equal to thickness of each wind. The discharge is given by capital Q is equal to pi d1 minus n into t b1 into v f1 and next formula, that is head on the turbine, is given by the equation capital H is equal to P1 divided by rho g plus V1 square divided by 2g, where P1 is equal to pressure at the inlet, where P1 is equal to pressure at the inlet. Now some points regarding Francis turbine. The inward flow reaction turbine having radial discharge at the outlet is known as Francis turbine, after the name of J.B. Francis, an American engineer who in the beginning designed inward radial flow reaction type of turbine. In the modern Francis turbine, the water enters the runner of the turbine in the radial direction at the outlet and leaves in the axial direction at the inlet of the runner. Thus, modern Francis turbine is mixed flow type of turbine. As in the case of Francis turbine, the discharge is radial at the outlet. The velocity of the whirl at the outlet, that is VW2, will be 0. Hence, the work done by the water on the runner per second, that will be equal to rho into Q VW1 U1. Work done per second per unit weight of the water striking, that will be equal to 1 divided by G VW1 U1, and the hydraulic efficiency will be given by the equation VW1 U1 divided by G into capital H. Now, some important relations for the Francis turbine. The ratio of the width of the wheel to its diameter is given as N is equal to B1 divided by D1, where the N varies from 0.10 to 0.40. Okay. The flow ratio is equal to VF1 divided by square root of twice GH, and the speed ratio is equal to U1 divided by square root of twice G H. So note down these formulas. Written? Now, today we will end our lecture here. In next lecture, we will see the numerical on the Francis turbine. Okay? Thank you. Have a nice day.